Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at the AQA A-Level Chemistry course and we're going to be doing the Introduction to Transition Metals and Complex Ions. So before we go on, don't forget to check the cards out in the top right hand corner here for links to other websites, and importantly, here you'll find the link to my new website, which we're going to have access to as of next week. We'll be running live webinars for your revision purposes. Do check the link out and come and see what's going on. But before we go any further, then let's just see what we should be able to do by the end of today's lesson. We should be able to identify transition metals and describe the properties of transition metals, recall some simple definitions of complex ions, identify the shape of complex ions based on the ligands attached to the metal, calculate the oxidation state of a transition metal given the formula of the complex. Let's have a look. So first up, what is a transition metal? Well, we've seen our layout of our periodic table before, where we've got the first two rows on the left here as our S block, because their outer electrons are in the S block, or our valence electrons. The D block elements in the middle here, where the outer electrons are in the D block, and the P block, where the outer electrons are in the P block. However, our transition metal is something a little bit more complex than simply just a D block element. We describe a transition metal as a metal that can form one or more stable ions with an incomplete D sublevel. So that's really important here when we come and talk about which of our elements are D blocks. So the first thing to remember is how we fill up electron shells from our AS. So in the 3D block, we have the 4s fills before the 3D, and 4s empties before the 3D in the ions. For example, chromium, we've also got as our two exceptions of chromium 4s1 3d5 and copper as 4s1 3d10. So let's just pull an example out. We'll do iron. We were going to give the electron configuration here for iron. Now I'm going to use a shorthand notation where we simply write the previous 1s2, 2s2, 2p6, 3s2, 3p6 as AR in square brackets, and then we have AR iron. We then have 4s2, and then we'd have 1, 2, 3, 4, 5, 6, 3d6. Now if we had Fe2+, in other words the ion of iron, the ion of iron, we'd have AR, and we've lost 2 electrons, but they, remember, the 4s fills before the 3D, and the 4s also empties before the 3D, so we end up here with 4s0, 3d6, because the 4s empties first. And then if we were to look at the other oxidation state here of iron, we'd have Fe3+, argon, we'd this time have 4s0, 3d5. Now, because we've got 4s0, there's no need to include that actually in the electron configuration. Now, the final thing to note here are those metals of zinc and scandium. Now, scandium, if we were to do the electron configuration, is argon 4s2 and 3d1, and scandium typically only exists as scandium 3+ as its common ion, and therefore has an electron configuration of just AR, 4s0, 3d1. Also zinc, if we were to look at the configuration here, we'd have AR, and that would be 4s2, 3d10. We typically only get zinc 2+, and therefore because we lose from the 4s first, we have 4s0, 3d10. You'll notice that both of these examples do not have an incomplete D subshell in its stable ions, and what that means is the scandium and zinc are not transition metals. Although they are in the D block, they are not transition metals. So they only exist here between titanium and copper. Let's now look at the properties of transition metals. So all transition metals show these four key properties. That is, we observe transition metals to form complex ions, and we'll be talking about those in a lot more detail later in this video. Coloured ions, they act as catalysts, and they all show variable oxidation states. Now all of these things essentially are interlinked, and we'll see how they explain the properties of the transition metals as we move through the following series of lectures. The rest of this lecture then looks at complex ions, and before we go and look at them, what we need to do is just come up with a few important definitions so we can understand really what we're talking about. These are all relatively new terms, so just be aware of what we mean here. The first here is a ligand, which is a particle with a lone pair, and that lone pair of electrons bonds to a metal by a coordinate bond. In other words, it's a bit like the dative covalent bond that we've seen before. Essentially, it's the same thing, where both electrons are coming from this thing called the ligand, and we're going to look at a variety of different ligands in just a moment. A complex, or a complex ion, is a metal central ion which has got coordinately bonded ligands, and we'll see lots of those as we go through this video. The coordination number is simply the number of coordinate bonds to the metal ion. Now this is important because it describes to us the shape and also the value of the coordination number, and the number of ligands can be different. And we'll see that later on, but the value of the ligands and the coordination do not have to be the same. And we've now got a slightly different description of an acid and base. Previously we talked about Bronsted-Lowry acid and base, where we described a proton donor and a proton acceptor, but a Lewis base we discuss as a lone pair donor. And we can see that really in a lot of the work we do here, but we can also describe Bronsted-Lowry bases as Lewis bases because they donate a lone pair of electrons to a proton. And we also have a description here of a Lewis acid, which here we're talking about, again, in terms of electrons, we're talking about a lone pair acceptor, which again, if you think about a hydrogen ion accepts a lone pair of electrons. So you can describe a hydrogen ion as a Lewis acid, but we tend to describe it as a Bronsted-Lowry acid. So our definition then of a complex ion was a metal ion with coordinately bonded ligands. Now here we got an example of a complex ion where we have our water molecules, that is H2O, datively covalently bonding to a central metal ion. Here in this case we've got Cu2+, and we represent the dative covalent bond here by the arrow, and it's coming from the lone pair of electrons. Now we write this molecule, or this complex, as follows. We write the metal atom to start with, and then in brackets we put in the ligand. So in this case we've only got one, so we simply write H2O. Next to it we write the number of ligands, and assuming we've got a charge, as we do here, we add in a square bracket around the formula and we put the charge on the outside. Another example that we could show is perhaps if we moved on here, and instead of having OH2s all the way around, or water molecules. Perhaps two of them, I'm just going to delete them out rather than draw it all again. Perhaps two of them are just OH. Now OH has got a 1 minus charge, so I'd then be able to write the formula of this new molecule as the central metal ion, copper, the ligands, which in this case are water, and now because I've removed two of the hydrogens from the waters, I now only have 1, 2, 3, 4 water molecules, and two of them here are OHs, that's another ligand, and I simply put the number next to it. This time there is no need for brackets because there is no charge on this substance, and in this case, because there's no charge, there's no need for the brackets. To move on to the shape of complexes, and there are 4 key shapes that we need to be aware of. This table here indicates the linear, square planar, tetrahedral and octahedral shapes, and indicates the coordination number. Remember, this coordination number is the number of coordinate bonds that are formed. So in this case, we've got the shape, and we're then indicating the transition metal in the center as M, and we've got our 4 different shapes. So the second line here, we've got a shape for linear of 180 degrees. That would be the bond angle. It's got 2 ligands attached to it, and an example here would be something like Ag plus complexes. And the reason that Ag plus tends to form linear complexes is simply its size. You can't get very many molecules around it, and the one that you will have come across, and the common one that we observe, is a Tollens reagent, which is Ag NH3. Now remember, we started off by saying the metal goes in the center, followed by the ligands. Because we've got 2 of them, we put a 2 in the brackets afterwards. Ammonia's got a neutral charge, so we need square brackets to indicate the positive charge. Examples of square planar complexes are platinum 2+, which we've seen before when we looked at cisplatin in our organic chemistry, as well as nickel 2+ tends to form square planar complexes. Again, we now have 4 ligands, so 4 attachments around the central metal atom, and our example here, we'll go with platinum. We're going to use a platinum tetrachloride, so that means 4 chlorines. That means we've got the ligands after the metal, we've got 4 of them. We've got a charge here, we've got platinum 2+, we've got 4 Cl-, so we've got Cl-. We'll come back to working out the oxidation states and the charge in a little while. If we have 4 ligands surrounding the central metal ion, this time as in a tetrahedral shape, then we would have a bond angle of 109.5 degrees. This tends to happen with larger charge ions like Cl-. So it's a larger charged ion, and that's simply because you can't get so many chloride ions around the central metal atom or ion. They are too large to fit. So an example here that you need to know, and we'll look at when we do the aqueous ion transition metals another day, would be copper tetrachloride. So copper again is a central metal ion. We've got 4 ligands of chlorides. The square brackets again because we've got a charge of 2-. The final example here is 1, 2, 3, 4, 5, 6 coordinate bonds, and this happens with most complexes that we find and most of the ones that you'll be dealing with. So all of the others really are exceptions that you simply need to know. Tend to happen with small ligands, and small ligands will tend to have things like ammonia or certainly nitrogen and oxygen attached. So H2O and NH3 tend to form, and OH minus we'll see in due course. An example, we'll carry on with our copper here with 6 waters, the copper coming first, then the ligands of water, 6 of them, square brackets because you've got a charge, and 2 plus. We call this the hexa because there's 6 of them, aqua because it's water, copper ion. Okay, so we've looked at the formation of complex ions and the shapes of complex ions along with the definitions. We're now going to look at some of the ligands that we will come across. And we describe these simply as something dentate. Dentate, and dentate coming from the word meaning for tooth. And we can imagine the tooth being the lone pair of electrons. So we have a variety of different types of ligands that we need to be aware of. The first, these first 3, well, we've actually got here, as well as we tend to see, so we get OH minus on this list, which is hydroxide. We also get ammonia, we get chloride ions, and we get water. These will form one dative covalent bond, and therefore we call these monodentate ligands. And we often, as we saw before, will get 6 of these around a metal ion, and they tend to form 6 coordinate bonds. The next sort here, we've got our two-toothed. So I'm just going to make this a bit bigger actually here. Put it down the bottom. So our example here, 1,2-diaminoethane. So each of these nitrogens can form a coordinate bond, and it's one molecule. So we've got 2 areas of teeth, and we therefore call these bidentate ligands, meaning two-toothed. Now, the next one here is ethane dioate. Now, the C double bond O doesn't tend to bond to the metal ion, but here, certainly the double bond, the lone pair of electrons with a negative charge do form a dative covalent bond with the metal ion, and we will form structures such as this chromium complex and this chromium complex here. The key here is these are both, as we look at them, 6 coordinate, and they both have a shape which is octahedral. Now that's because they each have 6 dative covalent bonds, but you'll notice here, if we look at the formula, we have chromium and we then have the diaminoethane, and the number of ligands here is only 3. So we've got 3 bidentate ligands here around each metal center, bidentate, forming a 6 coordinate octahedral shaped complex. Ethane dioate does the same. The final ones then to look at that we might be expected to recall are where we've got multiple points of contact. 2 classic ones that we look at in the course are EDTA4-. Now EDTA has got 6 points or 6 ligands. We got the O lone pair of electrons on the oxygen with a minus charge, and we also have this nitrogen here. So we have 1 ligand, but we have a 6 coordinate octahedral shape for this copper complex. So this is 1 ligand, but 6 coordinate. The other one we see here is porphyrin. We form 4 bonds, 1 from each of these nitrogens, and they tend to form around the central metal ion in a square complex shape. And this is classic for hemoglobin, where we have a large protein or globine molecule sat on one end of the ion. Then we have the porphyrin ring around the square planar, and then we have oxygen or water on the final position, which allows the absorption of oxygen and be passed around the blood in our bodies. These simply we describe as multidentate because they've got multiple points where we can bond to the metal center. We have multiple coordinate bonds from the one ligand. Before we look at the final thing on isomerism in complex ions, we'll just quickly identify how we can work out the oxidation state of a complex ion. The oxidation state of the metal ion is simply the total charge on the complex minus the sum of the charges of the ligand. So we'll look at a couple of examples here. We'll do copper H2O 6 2+. So in this example, the total charge of the complex is 2+, and the sum of the ligands, well, water is 0, so minus 0. So the oxidation state here of the metal is +2. Notice that oxidation states, we put the positive in front. We'll now move across and we'll have a look at, see what happens if we got CuH2O4OH. So we've now replaced 2 of our waters with 2OH. The total charge on the complex is 0, and the charges on the ligands, well, we got to take away -2 because OH is -1, so 0 minus -2 gives us +2. The final one then that we'll look at now is if we got, let's say, a chloride complex, CuCl4. Notice we've now got square brackets again. Previously we didn't because it was a neutral substance. We got 2-. The oxidation state on the metal, well, the overall charge on the total on the complex here is -2. Each chloride has got a -1 charge, so we minus -4, and we get a value of +2. The final thing we're going to look at in this video then is the stereoisomerism that we observe in complex ions. Now, the first example here we're going to look at is with square planar complexes, and we can observe here where we've got 2 of one type of ligand and 2 of another, and we can see that we got 2 ways of arranging those ligands. Now, if we have them opposite here, so we've got 2 Cl minuses and they are opposite one another in a square planar, then we describe this as trans isomerism. And if they're on the same side as we got on this one, then we have, this is described as cis. So this here is cis trans isomerism. We have already met this where we talked about this molecule here, which we describe as platin. And there are 2 examples of platin. It's the anti-cancer drug, and this one, because they're on the same side, is cis platin. Trans platin does exist, but is unable to effectively inhibit cancer. We also observe stereoisomerism in octahedral complexes, where we've got here 2 of one type of ligand and 4 of another, in these 2 nickel complexes. And in this example, again, we've got opposite, so this becomes our trans nickel H2O 4 OH2. Well, here we got them on the same side, so this becomes our cis nickel H2O4 OH2. Now, the cis trans is reasonably easy to identify as long as we realize these key components. The slightly more complicated one is the one we're going to move on to next. The final example then occurs when we've got the example here where we've got bidentate ligands, and these have the same formula, but different orientations in space. And these are now no longer cis-trans, but they become unable to be superimposed upon their mirror image. You may remember that as from your organic chemistry, we describe these here as optical isomers, as two non-superimposable mirror images. And if you can remember the term here, we describe these as enantiomers. Now, they're difficult to visualize and usually best just to try and make these if you've got some mods. But if you're trying to draw them, the best way to do is, as they've done here, is you sort of split your complex into two halves and draw one coming out and one going away on the left and right, and then fill in the other side. Just to recap then, firstly, don't forget to come along and check out Dr. Clay's A-Level Chemistry. It's at drclays-alevelchemistry.com, and you can find the link to my website in the cards here in the top right-hand corner. By the end of this lesson, you should now be able to identify transition metals and describe the properties of transition metals, recall some simple definitions of complex ions, identify the shape of complex ions based on the ligands attached to the metal, calculate the oxidation state of a transition metal given the formula of the complex, and we've also just looked there at the end of isomerism in complexes. I look forward to seeing you next time. Bye for now.